Today's topic is continuity and compactness. We will see how continuous functions defined on compact spaces play a very important role in topology. Today we will prove a very important theorem which states that every continuous image of a compact space is compact. Let us prove this theorem. For here we want to show that continuous image of a compact space is compact. So we need a compact space and we need a continuous mapping from a compact space to any topological space. So let X be a compact space and Y be any topological space, and let F is a mapping from X to Y, and this mapping is also continuous. And since we want to show that continuous image of a compact space is compact, so we have to show that F image of compact space, that is X, is compact. That is, we have to show that F of X is compact. Clearly mapping F from X to F of X. Here we have replaced Y by F of X. And F of X is nothing but the set of all those elements of Y which are image of elements of X. So this mapping is onto, and we note that this is also continuous because for any open set G in F of X, there exists an open set H in Y such that G is equal to H intersection F of X. Because F of X is a subspace, so we know that for any open set G in the subspace, there exists an open set H in Y such that G is equal to H intersection F of X. That means G contains all those elements of H which are in the image of X. And so if we take inverse image of G under F, then that will be equal to inverse image of H under F. And since mapping F is continuous, so we know that for any open set H in Y, F inverse H is open in X. And since F inverse H is equal to F inverse G, so for any open set G in F of X, F inverse G is open in X. So mapping F from X to F of X is also continuous. We want to show that F of X is compact, so we take any open cover of F of X and show that that open cover has a finite subcover. So let G lambda, lambda belongs to capital lambda, be an open cover of F of X where G lambda is open in F of X. Then clearly F of X is equal to union of G lambda. Lambda belongs to capital lambda. We mark it as 1. As F is continuous, so we know that F inverse G lambda is open in X for each lambda in capital lambda. As F is onto and F of X is equal to union of G lambda, so union of F inverse G lambda will form an open cover of X. And so from 1, it follows that F inverse of G lambda, lambda belongs to capital lambda, is an open cover of X. And so X can be written as union of F inverse G lambda, lambda belongs to capital lambda. As X is compact, so there exist finitely many sets F inverse of G lambda 1, F inverse of G lambda 2, up to F inverse of G lambda n, such that X is equal to union of F inverse of G lambda I varies from 1, 2, 3, 4 up to n. But since we know that union of F inverse of G lambda I varies from 1 to n is equal to F inverse of union of G lambda I varies from 1 to n. So X can be written like F inverse of union of G lambda I varies from 1, 2, 3, 4 up to n. If we take F image, then we get F of X is equal to union of G lambda I varies from 1, 2, 3, 4 up to n. because if we take F image of F inverse of union of G lambda I varies from 1, 2, 3, 4 up to n, then that will be equal to union of G lambda I varies from 1, 2, 3, 4 up to n because mapping is onto. So we have shown that any open cover of f of x has a finite subcover. So we have shown that f of x is compact. Hence, every continuous image of a compact space is compact. Now we have a corollary. Let x and y be topological spaces and f is a mapping from x to y and this mapping is continuous. If A is a compact subset of x, then f of A, that is continuous image of compact set A, is also a compact subset of y. Let us prove this result. We know that restriction of f, that is f restricted to A, is a mapping from A to Y, and we know that it is defined as f of A of x is equal to f of x for every x belongs to A is a continuous mapping. We have proved earlier that is restriction of a continuous mapping is also a continuous mapping. So FA from A to Y is continuous, and from the previous theorem it follows that f A of A, that is equal to f of A, is a compact subset of y, and so f of A is a compact subset of y. That means we have shown that continuous image of a compact subset is also a compact subset. Let us recall topological property. A property of a topological space is said to be a topological property if and only if every homeomorphic image of that topological space has that property. Now, we have a theorem which states that compactness is a topological property. Let us prove this theorem. Let X be a compact space and Y be any topological space, and F is a mapping from X to Y, and this mapping is a homeomorphism. By homeomorphism, we mean this mapping is bijective, this is continuous, and its inverse is also continuous. And since mapping is onto and this mapping is also continuous, so Y is a continuous image of X. And since continuous image of a compact space is compact, so Y is compact. Thus, every homeomorphic image of a compact space is compact. So, we can say that compactness is a topological property. Now, the next theorem states that let X be a compact space and Y be a Hausdorff space, then every bijective continuous mapping G from X to Y is a homeomorphism. Let us prove this theorem. As G is bijective and continuous, then to show that G is a homeomorphism, we have to show that G inverse is continuous. But we know that, and actually we have proved that G inverse is continuous is equivalent to say that G is a closed mapping or G is an open mapping. So it is sufficient to show that G is a closed mapping. That means we have to show that G image of any closed set in X is closed in Y. So let F be a closed set in X. We know that, and actually we have proved this result, that every closed subset of a compact set is compact. And here X is a compact space and F is a closed set in X. So F is a compact subset of X. As continuous image of a compact set is compact, we have just proved this result. So G image of F is a compact subset of Y. And we know that compact subset of a Hausdorff space is closed. We have proved this result earlier. And here, as Y is a Hausdorff space and G of F is a compact subset of Y. So by this result, G of F is a closed subset of Y, because compact subset of a Hausdorff space is closed. And so G of F is a closed subset of Y. So we have shown that G image of closed set F is closed in Y, and so G is a closed mapping, and hence G is a homeomorphism. Thank you.